This video is divided into 3 sections. The first section discusses strategies and practice problems for data representation. The second section presents strategies and practice problems for research summaries. Finally, the third section presents strategies and practice problems for conflicting viewpoints. This course is most effective if you use the student workbook that accompanies it. All of the problems discussed on the videotape are printed in the workbook. When a practice problem is presented on the screen, pause the videotape. Then, work the problem in the workbook. Finally, play the videotape to listen to an explanation of the correct answer. These problems were designed by Dr. Michael K. Smith, who has taught ACT review courses for over 20 years. We'll meet Dr. Smith later in the program. Let's begin our preparation for the science reasoning test by discussing data representation. Data representation problems present scientific information in the form of tables, graphs, or charts. Tables can be organized in different ways. For instance, a table could state the following. Information was collected on variables that affect the period of a pendulum. Table 1 presents information about a physics problem that involves the period of a pendulum. The table displays values for several variables that might affect the period of pendulum, such as mass, length, and starting angle. Let's look at a chemistry example. Table 2 presents information about the boiling point and melting point for various chemical elements. Graphs can also be presented in various ways. The graph could contain one variable on the x-axis and one variable on the y-axis. For instance, the following graph shows the relationship between the growth of bacteria in a cultured dish as a function of time. A graph might also have a second variable on the y-axis. For instance, the following graph displays the amount of carbon monoxide and carbon dioxide emissions as a function of time. The carbon monoxide scale is on the left side and is represented by a solid line. The carbon dioxide scale is on the right side and is represented by a dashed line. Scientific information can also be presented in charts. The following chart, for instance, presents information about the Pollution Standard Index, or PSI, a measure of air quality. The chart shows PSI levels, air quality, health effects, and environmental cautions. Note that charts can present information in a descriptive format instead of a strictly numerical format. That is, charts contain words as often as they contain numbers. No matter how the scientific information is presented, you must remember one important point. The answers to all the questions can be found by reasoning or problem solving from the material given. Let's talk about what you will be expected to do with these tables, graphs, and charts. There are 4 types of data representation questions. First, you will be asked to find information in the table, figure, or chart. For instance, what is the period of the pendulum when the length is 0.40? You might also be asked to find the sum or difference between 2 data points. Second, you will be asked to graph information. For instance, what is the best graph of the relationship between melting point and boiling point? Third, you will be asked to discover the relationship between 2 variables. There are 3 relationships that normally occur on science reasoning problems. First, 2 variables can have a positive or direct linear relationship. That is, as one variable increases, the other increases. For instance, in the physics problem, as length increases, so does the period of the pendulum. Second, two variables can have a negative or indirect linear relationship. In this case, as one variable increases, the other variable decreases. In the following graph, as the values of the x variable increase, the values of the y variable decrease. Finally, there can be no linear relationship between the two variables. That is, as one variable changes, another remains constant. In our physics example, for instance, as the period changed, the value of mass of the pendulum remained constant. Questions asking you to discover the relationship between two variables could be stated as follows. The evidence supports which of the following conclusions? The evidence supports which of the following hypotheses? Which of the following conclusions is supported by information in the table? Finally, you will be asked to predict new information. For instance, what is the length when the period is 1.50? To summarize, there are 4 types of data representation questions: finding information, graphing information, discovering the relationship between two variables, and predicting new information. Now let's join Dr. Smith as he discusses some data representation examples.
Hi, I'm Mike Smith. Here's how I'll approach the data representation examples. First, I'll read the problem set. You can follow along in the workbook. Then, I'll briefly overview the tables, graphs, or charts. Finally, I'll discuss one problem at a time. By using the workbook, you can work the problems with me. Now, let's start with problem set 1. Metabolic reactions, pain thresholds, and allergic responses are physiological functions in humans that follow a 24-hour cycle. Figure 1 displays the threshold of tooth pain in humans for 2 different stimuli: a cold stimulus measured in seconds and an electric current measured in milliamperes. Time of day is presented in military time units. 1,200 hours equals noon, 2,400 hours equals midnight. A threshold is the limit below which a stimulus is not perceptible or does not evoke a response. The pain threshold is defined as the minimum point at which the person reports any feelings of pain. Figure 2 presents the duration of feelings of numbness to tooth pain in hours after a set amount of anesthetic. Now, I like to look briefly at tables and figures before I start to answer questions. In Figure 1, the variable on the x-axis is time of day. The figure on the left side y-axis is length of stimulus measured in seconds. The right side y-axis indicates the variable electric current measured in milliamperes. The solid line represents the threshold for the cold stimulus. It corresponds to the left side of the y-axis. The dotted line is the threshold for an electric stimulus. It corresponds to the right side y-axis. Now, what is a threshold or a pain threshold? From the given information, a threshold is the minimum point at which a person reports feelings of pain. Let's look at Figure 1 to see if we can understand how to interpret it. For instance, at 1,200 hours, the length of a cold stimulus is about 4.5 seconds. This is the threshold for the cold stimulus. This means it takes about 4.5 seconds for a person to report any feelings of pain when a cold stimulus is applied. Figure 2 represents the duration of numbness in hours at various times of day after a person has been administered anesthetic. All right, we're ready to work the questions. Now remember, after I read a question, pause the video and work the problem yourself in the workbook. Then play the videotape and I'll explain the solution to the question. Question 1. At approximately 1,000 hours, feelings of pain would be reported to a cold stimulus after how many seconds? This question is asking us to find information from the figures. we want to use figure 1. Find 1,000 hours on the x-axis and then use the solid line which corresponds to the threshold for a cold stimulus. Read the number of seconds off the left side axis. At 1,000 hours, feelings of pain would be reported after about 4.5 seconds. The correct answer is D. Question 2. The information in figure 1 suggests that the lowest pain thresholds to an electric current occur. Once again, we're using figure 1. This time, however, we need to focus on the dotted line, the line that represents thresholds to an electric current. When do the lowest pain thresholds occur? This question corresponds to finding the lowest points on the graph. The lowest points on the graph occur in the hours after 0 and 0600 hours, and then after 2200 hours. Thus, the best answer is probably J, between the hours of 2200 and 0400. Question 3. The data in figures 1 and 2 support which of the following conclusions? Let's examine each conclusion. Pain thresholds increase throughout the day. From figure 1, we can see that thresholds actually increase through part of the day and then decrease. So option A is not true. We have the same problem with option B. Pain thresholds do not decrease throughout the day. They only decrease in certain parts of the day. Option C seems to be more accurate. Pain thresholds do increase and then decrease throughout the day, and this applies to both figure 1 and figure 2. Option D doesn't work. The graphs do not indicate that thresholds remain constant. Thus, the correct answer is C. Question 4. An anesthetic is administered for tooth pain at 1,500 hours. A person will report that the feelings of numbness have ended at approximately what hour? The question states that an anesthetic has been administered, so we need to use figure 2. At 1,500 hours, the duration of numbness is about 5 hours from the graph. A person would report that the feelings of numbness have ended at about 5 hours later. 1,500 hours plus 5 hours gives us 2,000 hours, or answer H. The correct answer is H. Question 5. The maximum pain thresholds for a cold stimulus and an electric current differ by approximately how many hours? We're back to using figure 1. What is the maximum pain threshold for a cold stimulus? From the graph, the maximum pain threshold occurs at about 1,000 hours. What is the maximum threshold for an electric current? This threshold occurs at about 1,800 hours. The difference between the two values is 8 hours. Thus, the correct answer is C. Question 6. Is the hypothesis all pain thresholds follow the same 24-hour cycle supported by the information in figures 1 and 2? One way to interpret this question is to consider if the graphs are identical. Do the thresholds for pain occur at the same times of day for both a cold stimulus and an electric current? From figure 1, we can see that this is not the case. Probably then either option H or J is correct. Option C provides the best explanation for why the pain thresholds do not follow the same 24-hour cycle. It seems that the maximum pain thresholds occur at different times for different stimuli. Thus, the correct answer is H. Question 7. An anesthetic administered for tooth pain produced feelings of numbness for approximately 2 hours. When was this anesthetic most likely administered? Let's use figure 2. An anesthetic was administered and produced feelings of numbness for 2 hours. Let's look at the y-axis, which has the variable related to duration of numbness. A value of 2 hours for duration of numbness corresponds to what time of day? If we draw a horizontal line, we can see that a value of 2 intersects the graph at approximately 2 time periods, about 0600 and 1800 hours. Looking at the answer options, the only value listed is 1800 hours. Thus, the correct answer must be D. Problem set 2. The electrical resistivity of copper alloys was investigated as a function of temperature. Copper was alloyed with either gold, nickel, or palladium, with varying percentages of copper contributing to the alloy. The alloy was then subjected to various temperature levels, and the resistivity in 10 to the minus 8 ohms per meters was measured. The data are presented in Table 1. Before we start the questions, let's look at the table. Across the top are temperatures, with the values increasing from 270 degrees Kelvin to 400 degrees Kelvin. The information along the side is divided into sections that differ by the percent of copper in the alloy. The percent of copper decreases from 99% to 70%. The same 3 copper alloys are repeated for each percentage. In other words, alloys of copper with gold, nickel, and palladium are presented at the different percentages of copper. Now finally, let's look at some of the numbers just briefly. Looking at the first copper-gold alloy at 99% copper, it seems that the numbers, or the electrical resistivity, increase as the temperature values increase. All right, we're ready to start the questions. Question 8. A 90% copper alloy has a resistivity of 7.08. What metal was the copper alloyed with, and at what temperature was the resistivity measured? This question is asking us to find specific information in the table. Let's focus on the part of the table that presents the 90% copper alloys. Scan the numbers and look for a value of 7.08. It appears that this value corresponds to a copper-palladium alloy at 300 degrees Kelvin. Looking at the answer options, the correct answer is H. Question 9. Which of the following generalizations about the relationship between temperature and electrical resistivity is supported by the data in Table 1? Well, we've actually already anticipated the answer to this question. From the first row of data, we noted that as temperature increases, so does electrical resistivity. Is this generalization supported by the rest of the data in the table? Yes, it is. A glance at the numbers in the other rows indicates that the values are increasing as temperature increases. Thus, answer A is the best choice. As temperature increases, electrical resistivity increases. Question 10. The electrical resistivity of a 70% copper-nickel alloy at 273 degrees Kelvin is approximately how many times greater than the electrical resistivity of a 99% copper-nickel alloy at 300 degrees Kelvin? To answer this question, we have to find 2 pieces of information in the table and compare them. First, the electrical resistivity of a 70% copper-nickel alloy at 273 degrees Kelvin. Looking at the table, find the intersection of 273 degrees and a 70% copper-nickel alloy. This value is 36.67. Circle this number or write it down. Next, find the electrical resistivity at 300 degrees for a 99% copper-nickel alloy. This value from the table is 2.91. So we're comparing 36.67 to 2.91. How many times greater is the first value? If we round the 2.91 to about 3 and the 36.67 to either 36 or 37, then it seems that the first value is about 12 times larger than the second value. Option H is the best answer. Options F and G are too small, and option J is too large. The correct answer is H. Question 11. Which of the following graphs expresses the relationship between electrical resistivity and the percent of copper in an alloy for a copper-gold alloy at 273 degrees Kelvin? For this question, we'll need information in the column labeled 273 degrees Kelvin. Let's be careful. The percent of copper alloyed with gold decreases as we go down the column. In other words, the first percent is 99, the next 90, then 80, and then 70%. What happens to electrical resistivity as we go down the column? It seems that the values increase from 1.73 to 7.12. What is the relationship between these two variables? It seems that as the percent of copper decreases, the electrical resistivity increases. Thus, our graph should express this type of decreasing linear relationship. The best option in this case is answer C. Question 12. At a temperature of 293 degrees Kelvin, what metal alloyed with 80% copper would produce a resistivity closest to the resistivity of a 90% copper-nickel alloy at 273 degrees Kelvin? This question requires us to find two pieces of information in the table. First, locate the value of a 90% copper-nickel alloy at 273 degrees Kelvin. From the table, this value is 13.69. Now let's focus on the 293 degrees Kelvin temperature column and the 80% copper alloys. Which of these three values is closest to the value of 13.69? It appears that only the copper-palladium alloy, which has a value of 12.12, is close to 13.69. Thus, the correct answer is F. Question 13. A copper-palladium alloy with an unknown percentage of copper was tested at 375 degrees Kelvin and found to have an electrical resistivity of 17.56. The percentage of copper in this alloy is probably... Well, this question is asking us to predict new information. We're given a new temperature value, one not in the table. This value of 375 degrees Kelvin is between 350 and 400 degrees Kelvin. The new value of electrical resistivity is 17.56, and we're focusing strictly on copper-palladium alloys. Looking at the table, a 99% copper-palladium alloy has a value of 2.92. A 90% alloy has a value of 7.74. An 80% alloy has a value of 12.87, and a 70% alloy has a value of 17.78. Our new value is 17.56, which is closest to the last value. The percentage of copper alloyed with palladium is probably about 70%. The correct answer is A. Question 14. An unknown alloy is composed of at least 70% copper. At temperatures between 273 degrees Kelvin and 400 degrees Kelvin, the electrical resistivity reaches levels no lower than 9.00. Based on the information in the table, which of the following metals could be this unknown alloy with copper? 1, gold, 2, nickel, 3, palladium. This is a difficult question. It states that the unknown alloy is composed of at least 70% copper. Well, this percentage applies to all the alloys in the table. All of them have at least 70% copper. Also, the problem states the temperature ranges are between 273 and 400 degrees Kelvin. The only values in this table are between these two values. Thus, in a way, the problem is telling us to look at the entire table. The electrical resistivity reaches values no lower than 9.00. Let's look at alloys of copper and gold first. From the table, it appears that the values of electrical resistivity for gold are never higher than 7.99. Thus, this unknown alloy cannot be gold, and we can eliminate Roman numeral 1. Thus, answer options F and J won't work. Could the unknown alloy be nickel? The values for nickel range from 2.71 all the way to 36.89. Some of these values are no lower than 9.00. Thus, the unknown alloy could be nickel as long as it's nickel with no more than 90% copper. So Roman numeral 2 works. How about an alloy with palladium? The values for palladium range from 2.10 to 17.78. So the unknown alloy could also be palladium. The best answer is H. Nickel and palladium could be the unknown alloy based on the information in this table. Problem set 3. Factors related to the absorption of sound in still air are presented in Table 1. The absorption rate, measured in decibels per thousand feet, is measured for sound waves of varying frequencies, measured in hertz, and in still air with different relative humidities. Humidity is a measure of the amount of moisture in the air. Table 2 presents the speed of sound in various media. The velocity of sound is measured in meters per second, and the density of the various media are measured in appropriate units. Now, once again, let's look at the tables briefly before answering questions. Table 1 has two variables: relative humidity, levels from 0% to 30%, and frequency, levels from 20 Hz to 4,000 Hz. The absorption rate of sound is measured at these various levels. Table 2 is more complicated. It presents the speed of sound and density levels for a variety of media, from gases to liquids to solids. Okay, let's discuss the questions. Question 15. At a frequency of 40 Hz, the absorption rate of sound was measured as 0.03 decibels per thousand feet. Most likely, what was the percentage of moisture in the air at the time this measurement was taken? This question asks us to find information in Table 1. Look at the row containing a frequency of 40 Hz. Scan the row for a value close to 0.03. At a humidity level of 30%, the absorption rate is 0.034. This is close enough. The correct answer must be D. Question 16. For frequencies between 20 and 100 Hz, which of the following expresses the relationship between humidity and absorption rate? Once again, we're using Table 1. Let's look at the row of data under 20 Hz. Here we notice that the absorption rate decreases from 0.154 to 0.009 as the level of humidity increases from 0 to 30%. We have evidence of an inverse relationship. Scanning the rows for frequencies from 40 to 100 Hz reveals the same pattern. The correct answer is G. As humidity increases, absorption rate decreases. Question 17. The relationship between speed of sound and density for the gases described in Table 2 can best be graphed as which of the following? Let's focus on Table 2, particularly the part related to gases. This relationship is more difficult to determine at first glance. The speeds of sound are not in any particular order. Our first task is to place some order on the values. Let's draw our own graph. The lowest speed of sound, 316 for oxygen, corresponds to the highest density, 1.429. The next highest value for the speed of sound, 331 for air, has a density of 1.293. The speed of sound for helium, 965, is related to a density of 0.178. Finally, the highest speed of sound, 1284 for hydrogen, corresponds to the lowest density, 0.90. Looking at our graph, it seems that there is an inverse relationship between speed of sound and density for gases. The best graph is contained in option C. The correct answer is C. Question 18. The relationship between speed of sound and density for solids, listed in Table 2, can best be described as which of the following? Let's look at Table 2 once again, this time at the part providing information for solids. Let's draw our own graph. Let's put the values of density in order on the x-axis from 2.7 to 11.4. Now locate the values for the speed of sound on the y-axis. Our graph goes down and then rises. Looking at the answer options, it appears that option D is correct. There is no apparent linear relationship between density and speed of sound. Question 19. Would the hypothesis absorption rate decreases as humidity increases be supported by the data in Table 1? This hypothesis seems to fit the data in Table 1. The values of absorption rate do decrease as humidity increases for most of the frequencies of sound. However, there is an exception, and this question is asking us to find this exception. Look at the data for 4,000 Hertz. Here the values for absorption rate increase up to 10% humidity and then decrease. Answer D is the best choice. Evidence in Table 1 does not support this hypothesis, and the values at 4,000 Hertz provide the main evidence against it. Question 20. The hypothesis speed of sound increases as density decreases is supported by data related to which of the following media? 1. Gases, 2. Liquids, 3. Solids. We've already seen from question 17 that there is an inverse relationship between speed of sound and density for gases, so Roman numeral 1 works. From question 18, we found that there is no linear relationship between speed of sound and density for solids, so Roman numeral 3 doesn't work. This information eliminates options H and J. Does this hypothesis fit the data for liquids? Looking at Table 2, it seems that the highest speed of sound, 1530 for seawater, corresponds to the highest density, 1.025. Furthermore, the lowest speed of sound, 1324 for kerosene, corresponds to the lowest density, 0.810. It does not seem that this hypothesis applies to liquids, given the information provided. So the only Roman numeral that works is 1. The correct answer is F.
Research summaries problems are organized as follows. A brief statement about the purpose of the experiments is given. For instance, researchers have hypothesized that several factors will affect the period of a pendulum. Then short summaries of 2 to 3 related experiments are presented. The summaries could be strictly verbal descriptions or could be accompanied by tables, figures, or charts. These tables, figures, and charts are presented in the same way as in data representation problems. There are 6 types of research summaries questions. First, you will be asked to find the purpose of the experiments. This question could be phrased as follows. What is the major hypothesis being investigated in this series of experiments? Second, you will be asked to find information in the experiments. The information can be found in the verbal descriptions or in the tables or figures. Third, you will be asked to evaluate conclusions. For instance, this question could be phrased in any of the following ways. Which of the following conclusions is supported by the results of the experiment? Do the results support the following statement? Which of the following best explains the results of the experiment? Fourth, you will be asked to compare and contrast experiments. This question could be phrased as, what is a characteristic common to the experiments? Or, on which of the following points do the experiments differ? Or, how was the experimental design different in Experiment 1 from Experiment 2? Fifth, you will be asked to graph the relationship between two variables, similar to data representation problems. Finally, you will be asked to predict new information. For instance, if the experiment were repeated with the following change, what would be expected? Or, if the following changes were substituted, what effect would that have on the experiment? Or, if the graph in the experiment were extended, what would be expected? In conclusion, there are 6 types of research summaries questions: finding the purpose, finding information, evaluating conclusions, comparing and contrasting experiments, graphing information, and predicting new information. Let's join Dr. Smith once again as he discusses several examples.
Problem set 4. Researchers hypothesized that the survival rate of certain species of moths would be influenced by various environmental conditions. Furthermore, they hypothesized that certain characteristics of moth species would allow them to adapt to specific environmental conditions, and the survival rate of these species would depend on these adaptations. Those moths with successful adaptations would evidence low levels of predation, that is, high numbers of moths would survive. A series of experiments was designed to test these hypotheses. Experiment 1. 2 sites were chosen which differed in industrial pollution levels. Site 1 had a low rate of pollution. Consequently, most tree trunks were close to their natural color. Site 2 had a high rate of pollution as measured by various indices. At this site, most of the tree trunks were blackened. A large number of pale moths and black moths were captured from other sites and tagged for identification. Equal numbers of pale and black moths were released at both sites. 2 weeks later, researchers recaptured as many moths as possible at both sites. The percentage of recaptured moths indicated the rate of predation. The data for this experiment are displayed in Table 1. Experiment 2. To investigate the effects of predator level, the experiment was repeated at 4 different locations. 2 of the sites were judged to contain a low number of predators that typically feed on moths, while another 2 of the sites were judged as having a high number of predators that typically feed on moths. Otherwise, the experimental procedures were the same as in Experiment 1. The data for this experiment are displayed in Table 2. Let's look at the experiments briefly before we start to answer the questions. These experiments investigated factors that influence the survival rates of different types of moths. Experiment 1 has 2 locations, Site 1 and Site 2, with 2 levels of pollution, low and high. The percentage of pale and black moths recaptured is the variable measured. Experiment 2 repeats Experiment 1, except that a new factor is added, predator level. Now let's discuss the questions. Question 21. Experiment 2 differs in its experimental design from Experiment 1, in that Experiment 2. Now, what is the main difference between the two experiments? Both experiments measure pollution levels. Both measure the percentage of pale and black moths recaptured. Experiment 2, however, adds a new factor, predator level. This addition is the main difference in design between the two experiments. Option A doesn't work. The procedures are the same. Option C is incorrect because only 2 levels of pollution are used in both experiments. Option D is incorrect because the percentage of moths recaptured is not part of the experimental design, but a result of the experiments. Answer B is the best choice. Experiment 2 did hypothesize that another variable, predator level, would influence moth survival. Question 22. Which of the following conclusions is supported by the data in Experiment 2? Looking at the answer options, we can see that option J is incorrect. At Site 5 and 6, more black moths are recaptured than pale moths. The other options suggest that one or more of the variables of pollution and predator level are influencing the percentage of black moths recaptured. If only one variable was affecting this percentage, then the other variable would have no impact. Now, how could this happen? If pollution level was the variable that mattered, then we would expect the same percentages of black moths recaptured at each pollution level. Thus, the percentages would be the same at the low levels. This is not the case. Since the percentages differ at all 4 sites in Experiment 2, this result indicates that both variables are important. Answer H is the best choice. Question 23. The highest percentage of pale moths that did not survive in Experiment 2 would be found at which of the following sites? Be careful with this question. It's asking us to determine the site in Experiment 2 in which the highest number of pale moths did not survive. The percentages in Table 2 indicate number of pale moths that did survive. To find the correct site, we need to choose the place where the lowest percent of pale moths was recaptured. This site would correspond to the place that had the lowest survival rate. The correct answer is D, Site 6. Question 24. Which of the following conclusions concerning pale moths is supported by the data in the 2 experiments? To me, it seems that option F is the most difficult to interpret. Let's look at the other options first. Option G is incorrect. From Table 1, we can see that pale moths adapt better than black moths at low pollution levels, but don't adapt as well at high levels. Option H is incorrect. From Table 2, the lowest percentage is for black moths at Site 4. Option J is incorrect. From Table 2, more black moths are recaptured at high pollution levels. The correct answer must be F. But why? The phrase holding pollution levels constant means to look only at sites where the pollution level is the same. From Table 2, let's look at Sites 3 and 4. The pollution level is constant. Both sites have low pollution levels. At these 2 sites, higher predator levels reduce the percent of both pale and black moths recaptured. Thus, the correct answer is F. Question 25. Which of the following graphs expresses the relationship between pollution level and the percent of pale and black moths recaptured in Experiment 1? We need to choose the graph that most accurately displays the information in Experiment 1. From Experiment 1, the percent of pale moths recaptured is about the same for both pollution levels. Only options A and C show constant levels for pale moths. At the high pollution level, more black moths are recaptured. This result is represented best by the graph in option A. The correct answer is A. Question 26. In experiment 2, the percentage of pale moths recaptured in conditions in which the pollution level was high and the predator level was low is approximately 1/2 the percentage of black moths recaptured under which of the following conditions? Looking at Table 2, the percentage of pale moths is 12.7 when the pollution level is high and the predator level is low. This percentage is approximately half of what black moth percentage? Well, 12.7 is about half of 25%. This percentage is close to the percentage at Site 5 for black moths. Site 5 has high pollution levels and low predator levels. Thus, the correct answer is H. Question 27. At what site would the lowest level of predation among black moths be found? Be careful with the wording. From the opening paragraph, we find that low levels of predation is equivalent to high numbers of moths surviving. From Table 2, the highest number of black moths survive at Site 5. Higher percentage of moths recaptured is the same as a high survival rate. Thus, the correct answer is B. Problem set 5. Researchers investigated factors that affect osteoporosis in adult women. Osteoporosis is a bone disease in which the bone mineral density decreases to such low levels that bones may be susceptible to fractures. Experiment 1. The average bone mineral density, BMD, was measured for samples of women at various ages. The fracture threshold is the point below which the likelihood of a bone fracture increases given the application of moderate stress. Data for this experiment are graphed in Figure 1. Experiment 2. Two groups of women, 50 years of age or older, participated in a study to determine the effects of exercise on changes in BMD. The exercise group participated in controlled aerobic exercises for a period of 1 hour, 3 times a week, for 12 months. The control group did not participate in controlled exercises. The percent change in BMD was measured at monthly intervals using 100% as the baseline measure. The data are graphed in Figure 2. Experiment 3. The BMD levels for a group of female athletes aged 50 or older were measured over a 6-month period. These women exercised an average of 7.5 hours per week in moderate to heavy aerobic exercises. The percent of BMD decreased over the 6-month period. These results are similar to studies done with younger male athletes. 3 different experiments present information on factors that influence osteoporosis in women. The first experiment graphs the relationship between age and bone mineral density, or BMD. The second experiment presents the change in BMD for 2 groups, an exercise group and a control group. Experiment 3 describes changes in BMD for a different group of women. Okay, let's discuss the questions. Question 28. Based on the data in Experiment 1, the maximum difference in bone mineral density between younger women and older women is approximately. This question asks us to calculate the difference between 2 sets of values. Using Figure 1, the highest value of BMD is about 0.99 for women aged 35. The lowest level of BMD is about 0.90 for women at an age of 70. The difference in these values is approximately 0.09. The correct answer is J. Question 29. Which of the following conclusions is supported by the control group results in Experiment 2? Well, what happened to the control group in Experiment 2? Looking at Figure 2, the percent of BMD declined over the 12-month period for the participants in the control group. The best conclusion is given in option B. The amount of BMD decreased. Thus, the correct answer is B. Question 30. A woman's BMD measurement is 0.88 grams per centimeter squared. Most likely, how old is the woman according to the data from Experiment 1? Using Figure 1, find the value of 0.88 for BMD on the y-axis. Draw a vertical line from this point until it intersects the graph. A value of 0.88 could be found in women at ages between 60 and 70. The best answer is J. An age of 63 would match the graph. Question 31. Over the past 12 months, a 60-year-old woman has exercised moderately for approximately 9 hours per week. According to the data from these experiments, it is likely that, well, which experiment provides information on women who exercise about 9 hours per week? Experiment 3 is the best choice. Women in this experiment exercise an average of 7.5 hours per week. What happened to their BMD levels? From Experiment 3, it seems that BMD levels decreased for these women. Thus, the best answer is B. Question 32. Suppose that the average BMD of the two groups of women in Experiment 2 was 0.90 grams per centimeter squared at the beginning of the study. Which of the following conclusions would be supported by the results of Experiment 2? From Figure 2, we can see that BMD levels increased for the exercise group and decreased for the control group. Options F and G are thus incorrect. Both options H and J mention the term fracture threshold. This term is to be found in Figure 1. The fracture threshold has a value slightly above 0.90. If the two groups of women had a BMD level of 0.90 at the start of the experiment, what would happen to this level as a result of exercise? From Figure 2, we can see that the value of BMD increased as a function of exercise. It's reasonable to conclude that the BMD level of 0.90 would increase as a result of exercise. The best answer is H. Question 33. Is the statement increases in the amount of weekly exercise will lead to increases in BMD supported by the results in all three experiments? Experiments 2 and 3 have information about weekly exercise. In Experiment 2, weekly exercise led to increases in BMD levels. In Experiment 3, however, the opposite result occurred. BMD levels decreased for women who exercise more hours per week. The statement, increases in the amount of weekly exercise will lead to increases in BMD, is not supported by Experiment 3. Thus, options A and B are eliminated. The best answer is D. The main reason this statement is not supported is given in option D. Because the women in Experiment 3 showed decreases in BMD at higher exercise levels. Once again, the correct answer is D. Question 34. The researchers hypothesized that changes in both exercise and diet would increase the BMD of women over 50. Specifically, they felt that the addition of a dietary supplement, such as calcium, would increase BMD levels. Which of the following changes in experimental design would best test this hypothesis? The researchers feel that another variable, in addition to exercise, will affect BMD levels. We need an experiment that will allow us to compare exercise and dietary supplements together. We would need to redesign one of the experiments. Options G, H, and J introduce comparisons of men and women. This comparison is not necessary. The researchers are only interested in comparing exercise and diet for women over 50. Thus, we can eliminate these three options. Option F must be the correct answer. By modifying Experiment 2 to include an exercise and control group that did and did not take calcium supplements, we can make the appropriate comparison. Thus, the correct answer is F. Problem set 6. Changes in altitude can produce changes to the muscular, cardiovascular, and respiratory system in humans. Several experiments were conducted to determine how changes in altitude affect human performance. Experiment 1. Sudden exposure to certain altitudes can produce a rapid loss of consciousness in humans. This is particularly apparent in people who have not been acclimatized. That is, people who have not been given time to adjust to the higher altitude. The effect of sudden exposure to various altitudes on unacclimatized subjects was measured, and the results presented in Figure 1. Experiment 2. The heart rate at different work rates was measured for one subject at both sea level and at an altitude of 5,800 meters. The subject had a period of 2 weeks to be acclimatized at the 5,800 meter altitude before the experiment began. The results are presented in Figure 2. Experiment 3. The effects of altitude on the speed of athletic performance were tested. Athletes were timed running at 5 different intervals, 100 meters to 1,500 meters, and at 5 different altitudes, sea level to 4,000 meters. The percent increase or decrease in athletic speed was measured relative to sea level performance. The data are presented in Table 1. Well, here we have 3 experiments demonstrating how changes in altitude affect human performance. Experiment 1 shows how long it would take to lose consciousness given sudden exposure to various altitudes. Experiment 2 shows changes in heart rate due to different work rates for 2 different conditions, sea level and an altitude of 5,800 meters. Experiment 3 shows the effects of different altitudes on athletic performance, specifically changes in running speed at different distances. Okay, let's discuss the questions. Question 35. A person suddenly exposed to an altitude of 8,000 meters would lose consciousness in approximately how many minutes? Using Figure 1, locate an altitude of 8,000 meters. A horizontal line from this point would intersect the graph at a value of 4 minutes. The correct answer is B. Question 36. At an altitude of 2,000 meters above sea level, an athlete's performance running 200 meters would be closest to his or her performance running what distance at an altitude of 3,000 meters above sea level? Let's use Table 1. At an altitude of 2,000 meters and a distance of 200 meters, the value in the table is 102.1%. At an altitude of 3,000 meters, what distance is closest to this value of 102.1%? Scanning the row of percents, we can see a value of 102 for 100 meters. This value is closest to 102.1. Thus, the correct answer is F. Question 37. At a work rate of 1,200, an individual's heart beats 175 times per minute. At what altitude was this measurement probably taken based on the information in the experiments? Let's use Figure 2. Locate the intersection of a work rate of 1,200 and a value for heart rate of 175 beats per minute. These two values intersect only one of the lines, that for the sea level condition. The correct answer must be A. Question 38. Which of the following conclusions is supported by the results of Experiment 2 concerning human performance at an altitude of 5,800 meters? Let's use Figure 2 and let's focus only on the dotted line, the one representing performance at 5,800 meters. What happens to heart rate as work rate increases? Looking at this figure, we can see that heart rate initially increases and then stabilizes or becomes constant. The best answer is F. As work rate increases, heart rate first increases and then becomes constant. The correct answer is F. Question 39. From experiment 2, the heart rate at a work rate of 300 for the subject at an altitude of 5,800 meters is equivalent to what work rate at sea level? Let's use figure 2. Locate a work rate of 300. Draw a vertical line that intersects the dotted line. The value is approximately 150 beats per minute. This value of 150 beats per minute corresponds to what work rate at sea level? Draw a horizontal line from 150 heartbeats until it intersects the solid line. Then read the value of work rate, which is 900. The correct answer is C. Question 40. Which of the following graphs expresses the relationship between altitude and percent change in athletic performance for runners at a distance of 800 meters? Let's use Table 1. Locate the information in the column labeled 800. The values in this column decrease from a percent of 100 at sea level to a percent of 93.5 at 4,000 meters. In other words, as altitude increases, the values for athletic performance decrease at 800 meters. Option J is the best graphical representation of these values. The correct answer is J. Question 41. Which of the following conclusions is supported by the results of Experiment 3? Once again, let's use Table 1. What happens to athletic performance as the altitude increases? At distances of 100 meters, the percents increase, as they do at 200 meters. At 400 meters, however, the percents increase and then decrease. At distances of 800 and 1,500 meters, the percents strictly decrease. It seems that option D is the best choice. As altitude increases, athletic performance increases at shorter distances and decreases at longer distances. The correct answer is D. Question 42. At an altitude of 2,000 meters, an athlete running a distance of 900 meters would probably notice what percent change in his or her athletic performance relative to sea level. Let's use Table 1. This question asks us to predict new information. For an altitude of 2,000 meters and a distance of 800 meters, the value in the table is 98%. For an altitude of 2,000 meters and a distance of 1,500 meters, the value is 95%. The distance of 900 meters is just a little above 800 meters. We would predict that the percent would be between 98 and 95%, and probably closer to 98%. Let's say the percent is 97. Now this figure represents a speed that is 97% of the speed at sea level. So what is the change? Well, there's been a change from 100% to 97%, or a decrease of 3%. The correct answer is G.
Conflicting viewpoints problems are organized as follows. A general statement about some hypothesis that is being investigated is presented. Then two scientists debate the hypothesis. The two scientists will always disagree with each other. This type of problem tests your ability to determine the main points of each scientist's argument and the evidence supporting his or her argument. There are 6 types of questions. First, you will be asked to determine if a particular conclusion supports scientist 1 or scientist 2. Second, you will be asked to evaluate whether new evidence supports scientist 1 or scientist 2. For instance, Which of the following discoveries would support scientist 1's argument? Third, you will be asked to evaluate whether new evidence would weaken the argument of scientist 1 or scientist 2. For example, a sample question might be, which of the following pieces of evidence, if discovered, would weaken scientist 2's argument? Fourth, you will be asked to determine a point of agreement between the two scientists. For instance, a question might be phrased as, on which of the following points would scientist 1 and scientist 2 agree? Fifth, you will be asked to determine a point of disagreement between the two scientists. For instance, scientists 1 and 2 would not agree about which of the following points. Finally, you will be asked to determine assumptions supporting the theories. A typical question might be as follows. Scientist 1 has assumed which of the following in developing his or her argument? To summarize, there are 6 types of conflicting viewpoint questions: conclusions, supporting evidence, weakening evidence, points of agreement, points of disagreement, and assumptions. Let's join Dr. Smith as he discusses a sample passage.
Problem set 7. Over 15 million years ago, an asteroid hit the Martian surface, flinging rocks into space. One particular meteorite, ALH 84001, fell on Antarctica 13,000 years ago and was discovered recently by geologists. The meteorite has undergone extensive testing for signs of possible life. 2 scientists discussed the possibility that there is evidence of life to be found in this sample of rock from the planet Mars. Scientist 1. There are several pieces of evidence which support the conclusion that ALH 84001 contains signs of microbial life. First, the rock contains tiny globules of carbonates, probably formed when carbon-rich water, a prerequisite for life, flowed through the rock. Second, the rims of the globules are coated with iron sulfide and other minerals which can be produced by bacteria. Third, the globules contain what appear to be nanofossils, tiny elongated and ovoid forms resembling fossils left by bacteria on Earth. Finally, the rock compounds contain polycyclic aromatic hydrocarbons, or PAHs, which often have biological origins. The concentration of PAHs increased as the interior of the meteorite was analyzed. If the PAHs were due to earthly contaminants, then their concentration should have been largest at the surface. Studies from sites on Earth have found concentrations of microfossils and tiny bacteria identical to those found in the meteor. These specimens were discovered in harsh environments, suggesting that the life forms in this meteorite could have survived in similar circumstances. The development of new technology, which could detect preserved microbial cell walls in the fossils, should lend support to this argument. Scientist 2. There is no conclusive evidence that signs of life on Mars are found on the meteorite ALH 84001. The meteorite has probably been contaminated by earthly substances. For instance, PAHs are associated with coal and diesel exhaust, contaminants which could have affected the meteorite. PAHs are also abundant in ancient sedimentary rocks and the residue of chemical changes that occurred to dead marine plankton and plant life that were the source of these rocks. The same PAHs are found in meteorites that did not come from other planets and which were formed too early in the history of the solar system for life to have come into existence. Furthermore, the supposed fossils have internal structures that more closely resemble crystals of iron oxide rather than small bacteria found on Earth. The minerals in the meteorite were formed at temperatures as high as 1400 degrees Fahrenheit, circumstances much too hot to have supported biological processes. even if new technology indicates the presence of cell walls, it will be difficult to determine whether the bacteria came from Mars or were formed after the meteorite fell to Earth. Scientist 1 strongly supports the position that this meteorite contains signs of life on Mars. Scientist 2, however, states that there are no conclusive signs of life on Mars contained in the meteorite. This scientist suggests that all indications of extraterrestrial life can be explained away. Let's discuss the questions. Question 43. The statement, "When tested, many meteorites from other planets contain minerals of earthly origin," would support. Well, Scientist 2 argues strongly that minerals on meteorites come from earthly sources. This scientist says the meteorite has probably been contaminated by earthly substances. Thus, meteorites containing minerals from Earth would probably support Scientist 2. Option D is the best choice. The presence of these minerals would be indications that the meteorites were contaminated after they landed on Earth. The correct answer is D. Question 44. Which of the following pieces of evidence would not support Scientist 1's theory? Let's examine each option. Option F states that the concentration of PAHs is largest on the surface of the meteorite. Scientist 1 would not like this discovery. This scientist states the following: if the PAHs were due to earthly contaminants, then their concentration should have been the largest at the surface. If new testing indicated that this was true, then Scientist 1 is in trouble. Option F is probably correct. Let's quickly look at the other options. Scientist 1 would like the discovery of nanofossils on other Martian meteorites. It would support the contention that this meteorite had nanofossils. Scientist 1 would like the evidence in option H and J. The existence of bacteria at temperatures over 1400 degrees would dispute Scientist 2's contention that biological processes can't survive at these temperatures. And Scientist 1 also would like a higher percentage of carbonates. This fact supports his argument for life existing in the meteorite. The correct answer is F. Question 45. Which of the following pieces of evidence would not support Scientist 2's theory? Let's examine each option once again. Scientist 2 believes the meteorite has been contaminated. Thus, option A would support this opinion. Also, Scientist 2 argues that the supposed fossils have internal structures similar to iron oxide. So option D would support this view. Scientist 1 needs to argue that nanofossils can also be extraterrestrial in origin. So, if option C is true, Scientist 1 is weakened and Scientist 2 supported. Thus, the correct answer must be option B. If there were no signs of plant life in Antarctica where the fossil was found, this would weaken Scientist 2's argument that PAHs could be due to plant life. Thus, the correct answer is B. Question 46. Both scientists assume which of the following? An assumption is a fact or condition that has been taken for granted. What do both scientists assume? Scientist 2 would not agree with option F. This scientist argues that the PAHs could be crystals of iron oxide instead of remnants of bacteria. Also, Scientist 2 would disagree with option G. Both scientists would agree that technology can determine the composition of meteorites. Scientist 1 argues that new technology would help the argument, while Scientist 2 suggests that new technology will support the opposite position. Both scientists assume that testing will determine the composition of meteorites. They only disagree about the interpretation of this composition. Finally, only Scientist 1 argues that nanofossils can be left by bacteria on Earth. The correct answer is H. Question 47. Scientist 1 and Scientist 2 would agree on which of the following points? Scientist 2 would not agree with option A. Scientist 2's argument depends on stating that meteorites can be contaminated. Scientist 2 would also disagree with option B. At certain temperature levels, biological processes cannot be supported. Scientist 2 would agree with option C, but Scientist 1 wouldn't. Scientist 1 argues that the nanofossils are evidence of life, not just mineral deposits. Both scientists agree with option D. PAHs have biological origins and are found in earthly bacteria. The correct answer is D. Question 48. Scientist 1 and Scientist 2 would disagree on which of the following points. Both scientists agree that some meteorites can be contaminated. Even Scientist 1 suggests that some PAHs can be caused by earthly contaminants. Both scientists disagree with option G. Scientist 2 argues that the biological processes cannot be supported at high temperatures. Scientist 1, however, argues that bacteria can survive in harsh environments. We don't know if Scientist 2 would disagree with option H. Scientist 2 is arguing that this particular meteorite doesn't have signs of extraterrestrial life. We don't know if the scientist believes that no meteorites can contain signs of such life. Scientist 2 actually agrees with option J. The same PAHs are found in meteorites that did not come from other planets. Thus, the correct answer is G.